Hello everyone. In this video we are going to discuss about BJT, bipolar junction transistor. Bipolar junction transistor is generally a three terminal device. The three terminals are emitter, base and collector. The doping concentration of these three regions, emitter, base and collector, are different. The emitter region is heavily doped and the collector region is moderately doped and the base region is lightly doped. The doping concentration of collector is less than emitter and the doping concentration of base is less than the collector. BJT is generally a current control device. BJT is a current control device, whereas MOSFET is a voltage control device. BJT is a current control device because the output of BJT is controlled by the current in the circuit. BJT is an active device. There are two types of devices called active devices and passive devices. Generally, the resistors comes under passive devices and the BJT transistors comes under active devices because the electron flow in the circuit is controlled electrically. In a transistor, the electron flow in a circuit is controlled electrically. Therefore, BJT is an active device. Bipolar junction transistor has its name bipolar because its operation involves two kinds of charge carriers, both the electron and holes. The operation of BJT depends on both the electrons as well as holes. Therefore, it has its name bipolar, two poles, bipolar junction transistor. The construction of BJT is discussed in this slides. There are two types of transistors called PNP transistors and NPN transistor. This P denotes the p-type semiconductor and the N denotes the n-type semiconductor. For PNP transistor, n-type semiconductor is sandwiched between two p-type semiconductor. This n-type semiconductor is sandwiched between two p-type semiconductor. This p-type semiconductor acts as an emitter and this p-type semiconductor acts as the collector. Generally, the emitter and collector will be of same type of semiconductor and the base will be of different type of semiconductor. This n-type acts as the base. Thus, three terminals, emitter, base and collectors are obtained. There are two PN junctions in a bipolar junction transistor. First one, this emitter and base junction. This forms a PN junction, and the next PN junction is the base collector junction. This junction between the P and N type. This is for PNP transistor. Next one is NPN transistor. For an NPN transistor, the p-type semiconductor is sandwiched between two n-type semiconductor. This n-type forms the emitter, this n-type forms the collector, and the p-type forms the base of a bipolar junction transistor. Here also there are two PN junctions. One corresponds to the emitter base and next one corresponds to the base collector junction. This bipolar junction transistor is also called as minority carrier device. This bipolar junction transistor is also called as minority carrier device because the current flow in the circuit in this BJT is due to the minority charge carriers and not because of majority charge carrier. The current flow is due to the minority charge carrier and hence the name minority carrier device. For an NPN transistor, the minority carrier is electron, and for a PNP transistor, the minority carrier is holes. This bipolar junction transistor BJT could also be called as this current control device. It is a current control device as well as it is a minority carrier device. BJT is a minority carrier device as well as current control device. This is the circuit symbol for the BJT. For PNP transistor, this is the circuit symbol. We could identify the transistor, the type of transistor, whether it is NPN or PNP from the circuit symbol. If the arrow in this, the arrow mark in this emitter region, if it is towards the base, then it is called PNP transistor. If it is away from the base, then it is called NPN transistor. This arrow mark denotes the direction of conventional current. Usually, this is the circuit symbol for a BJT. The leg with arrow mark denotes the emitter and the opposite to emitter is collector, and in between emitter and collector is the base terminal. The arrow mark in this emitter terminal denotes the direction of conventional current. This is the important point to be noted. The arrow mark in the emitter leg denotes the direction of conventional current. If this arrow mark is towards the base region, then it is called PNP transistor. If it is away from the base region, it is called NPN transistor. Generally, the emitter and base region are forward bias, and base and collector region are reverse bias. Emitter base junction are forward bias, and base collector junctions are reverse bias. This is a PNP transistor. This is the emitter is of P type, base is of N type, and collector is of P type. For forward bias, positive terminal of the power supply has to be connected to P type. So the positive terminal is connected to the emitter and the negative is connected to the base. Thus, emitter base junction is forward bias. This emitter is of P type, so the positive terminal is connected to the emitter and the negative is connected to the base. The collector is of P type. Since collector base junction is to be reverse bias, negative terminal is connected to the P type. In order to apply reverse bias, negative terminal is connected to the P type and the positive terminal is connected to the base. Thus, the emitter base junction is forward bias and the collector base junction is reverse bias. In case of NPN transistor, emitter is N and collector is also N, base is of P type. For the emitter and base to be forward bias, negative terminal is connected to the N type. Negative terminal is connected to N type and the positive terminal is connected to base junction. Collector is of N type. For collector base junction to be reverse bias, positive terminal is connected to the collector and the negative is connected to the base. For the P type to be forward bias, positive terminal is to be connected. For the N type is to be forward bias, negative terminal is to be connected. For P type to be reverse bias, negative terminal has to be connected. For the N type to be reverse bias, positive terminal has to be connected. The voltage across emitter and base is denoted by VEB. The voltage across base collector is denoted as VCB, and voltage across emitter and collector is denoted as VCE. For an NPN transistor, when the emitter junction is forward bias, emitter base junction is forward bias, the electrons start flowing towards the base. For an NPN transistor, when emitter and base junction is forward bias, the electrons from N type will move towards the base, and since base is of P type, the majority carriers will be holes, and it is not heavily doped, it is lightly doped, so there will be less number of electrons, less number of holes. These electrons from N type will recombine with the holes. Only small number of recombination takes place, and the remaining number of electrons will flow from base to the collector, which constitutes a current called collector current. This flow of electron constitutes a current called emitter current, and the recombination constitutes the base current, and the remaining electron that flows to the collector circuit constitutes the collector current, which is denoted as IC. This is given in this slide. The electron starts flowing towards the base, which is lightly doped. Only few electrons would recombine with the base holes. Since there is less number of holes in this base region, only few electrons will recombine with those holes, and the rest of them would then travel to the collector, and the remaining electrons which are not recombined will move to the collector junction. The current is due to the minority carriers, so it is called as minority carrier device. Generally, there are three operating regions: active region, saturation region, and cutoff region. This is the output characteristics of the BJT. This region is called the active region. In this active region, the transistor will operate as an amplifier. In this saturation region, the output will be maximum. The transistor will act as a switch which is in on state. In saturation region, the transistor will act as a switch which is in on state. In cutoff region, the transistor will act as a switch which is in off state. Since there are two states for a BJT, on and off, this could be used as a switch. The BJT is used as a switch in saturation region and cutoff region, and it is used as an amplifier in active region. BJT is used as an amplifier in active region. It is used as a switch in saturation region and cutoff region. In saturation region, BJT is considered to be in on state, whereas in cutoff region, BJT is considered to be in off state. BJT is considered to be in off state. These are the two main applications of BJT. It could be used as a switch or it could be used as an amplifier. There are three configurations, namely common base, common emitter and common collector. This is the common base configuration. In common base configuration, the base terminal is grounded. The base terminal is grounded. The arrow mark is towards the base, so it is of PN. So it is a PNP transistor. Emitter is P, base is N, and collector is P. Now let us bias the transistor. Emitter and base region has to be forward bias. So positive terminal is connected to the emitter junction and the negative terminal is connected to the base junction, and this base junction is this base terminal is grounded. This base terminal is grounded, hence the name common base. And the collector base junction has to be reverse bias. So the negative terminal is connected to the collector and the positive terminal is connected to the base. In common base configuration, input is applied between emitter and base. Input is applied between emitter and base, and the output is obtained between base and collector. So this base is used as a common terminal for both the input and output. Input is applied between emitter and base. Base involves in input port also, and the output is taken between collector and base. Here also the base port involves. So it is called as common base configuration. This is the input signal which is being applied. One biasing resistance R in. Let us calculate the gain for this common base. Gain is nothing but this is the voltage gain AV, which is nothing but output voltage divided by input voltage. The output voltage is given as V out and the input voltage is given as V in. V out by V in. V out is calculated using IC into RL. From Ohm's law, V equal to IR. So the voltage drop across this resistance RL is nothing but the current through this resistance and the value of the resistor. So IC into RL. V out equal to IC into RL and V in equal to IE into RIN. V equal to IE into RIN. V in equal to IE into RIN. This IC by IE is called as current gain of common base configuration. This IC by IE is the current gain of common base configuration. This is denoted by alpha. Then the RL by RIN is the resistance gain. This is the voltage gain. Together this is the voltage gain, and IC by IE is the current gain. RL by RIN is the resistance gain. This is the input and output characteristics for the common base configuration. The input configuration for an input characteristics, the input current IE and input voltage VBE are plotted. In x-axis, the input voltage VEB is plotted, and in y-axis, the input current IE is plotted. The variation of IE with respect to VEB is plotted while changing the value of VBC. By changing VBC, the variation of IE is noted. By changing VBC, the variation of IE is noted. For an output characteristic is plotted between VBC and IC by varying the value of IE. VBC is plotted in the x-axis and IC is plotted in the y-axis, and the value of IE, input current, is changed. Let us consider this input characteristics of common base configuration. First, the value of VCB is kept as constant as 0 volt. Then the VEB will be changed from 0 to 50 millivolt, and the corresponding value of IE will be noted, and this value forms this arc. Then the VCB will be changed to 10 volt, and then the VEB will be increased from 0 to 50 millivolt, and corresponding IE will be noted, and that value is plotted to obtain this arc. This is how we get the input characteristics of common base configuration. Next, for output characteristics, first initially the IE value is set to 0 millivolt, then the VCB is increased from 0 and the corresponding value IC is noted. Next, IE is set to 1. Similarly, the VCB is increased from 0 and the corresponding output current IC is noted. This is the output characteristics of common base configuration. Next is the common emitter configuration. In this, the emitter terminal is grounded. The arrow mark is away from the base junction, so it is of NPN type. N, base is of P, and collector is of N. It is of NPN transistor. So we know that emitter base junction has to be forward bias. So the negative terminal is connected to the emitter and the positive terminal is connected to the base. Similarly, the collector has to be reverse bias. So the positive terminal is connected to the collector and the negative terminal is grounded. The input, since common emitter configuration, emitter port will be common to both the input as well as output. The input is applied between base and emitter. And the output is obtained between collector and emitter. We have seen that alpha equal to IC by IE in the previous configuration called common base configuration. And for common emitter configuration, the current gain is denoted by beta and is nothing but the output current IC divided by the input current IB. So it is given as IC by IB. From this equation, alpha equal to IC by IE, we get this equation IC equal to, if we cross multiply, we get IC equal to alpha IE. So from alpha we could derive that IC equal to alpha IE. From this equation we could get that if we cross multiply beta and IB, we get IC equal to beta IB. This is the equation for IC in terms of alpha as well as beta. Now let us substitute this equation IC in both alpha and beta. In this equation alpha equal to IC by IE. In place of IC we are going to substitute beta IB. So in place of IC we are substituting beta IB, and for IE we know that IE, emitter current IE, equal to collector current IC plus base current IB. So instead of IE we will be substituting IC plus IB. In place of IC we will be substituting beta IB. In place of IC we will be substituting beta IB. Then for this IB we are just using it as IB. and now we will be taking out IB as common. So this IB and this IB will get cancelled. So and the final equation will be equal to beta divided by beta plus 1. So alpha is equal to beta divided by beta plus 1. And for this equation beta equal to IC by IB, in place of IC we will be substituting alpha IE. In place of IC we will be substituting alpha IE, and in place of IB, from this equation we know that IB equal to IE minus IC. IE minus, in place of IC we will be substituting alpha IE. If we take IE as common, in IE numerator and denominator will get cancelled, and we get the final equation as beta equal to alpha by 1 minus alpha. This is alpha in terms of beta, and this is beta in terms of alpha. This is the input and output characteristics for the common emitter configuration. For common emitter configuration, emitter terminal will be common for both input and output. So emitter will be present in both input as well as output. And base junction will act as an input, and collector junction will act as an output. Collector will be used as an output and base will be used as an input. So the input characteristic is plotted between input voltage VBE and input current IB. Input voltage VBE and input current IB. By keeping output voltage VCE as constant. By keeping output voltage VCE as constant. Initially the output voltage VCE is kept at 10 volt. It is constant 10 volt. Then the value VBE input voltage is varied and its corresponding input current IB is noted. This is how input characteristics for common emitter configuration is obtained. For output characteristics of common emitter configuration, the graph is plotted between output voltage VCE and output current IC with constant input current IB. With constant input current IB. So the output characteristic is obtained by plotting output voltage VCE versus output current IC with constant input current IB. This is the input and output characteristics for common emitter configuration. Next configuration is the common collector configuration. In this configuration, the collector terminal is grounded. For biasing condition, we know that base and emitter region has to be forward bias. So for the base has to be forward bias. The base is of P type. For in an NPN transistor, base is of P type material. So to apply forward bias for the base, positive terminal of the battery is connected to the base and the negative terminal is grounded. And for the emitter region to be forward bias, emitter is of N type. So the negative terminal of the battery is connected to the negative terminal of the power supply is connected to the emitter terminal, and the positive terminal is grounded and the collector is grounded. This is called as common collector configuration because the collector terminal is common for both the input as well as the output. So this is called as common collector configuration. The current gain of common collector configuration is given as IE divided by IB because the output current is IE and the input current is IB. IE divided by IB. We know that this relation IE equal to IC plus IB. So instead of IE, we are substituting IC and IB. This IB is common for this term as well as this term. So IC divided by IB plus 1. We know IC divided by IB is nothing but beta. So AI equal to beta plus 1. For common collector configuration, the current gain could also be denoted as gamma. So gamma equal to beta plus 1. Base will be the input and emitter will be the output, with collector being common to both the input as well as the output. This is input and this is output. The input characteristic is plotted with the input voltage VBC versus input current IB with constant output voltage VEC with constant output voltage VEC. The output characteristic is plotted with output voltage VEC versus output current IE with constant input current IB. This is the input and output characteristics for common collector configuration. Each of these configuration, common base, common collector and common emitter, has a specific application according to their characteristics. This is the comparison between the common base, common emitter and common collector. The first parameter is input impedance. Common base has low input impedance and common collector has high input impedance, with common emitter has medium input impedance. For output impedance, common base has high output impedance, common emitter has high output impedance and common collector has low output impedance. Phase shift is nothing but the phase shift between the output and input current and voltage. There is no phase shift in common base and common collector. In case of common base and common collector, there is no phase shift, but in case of common emitter, the phase shift is 180 degree. The next three parameters are voltage gain, current gain and power gain. Common base has high voltage gain, common collector has high current gain and common emitter has high power gain. This is an important point to be noted. Common base has high voltage gain, common collector has high current gain and common emitter has high power gain. So in case of amplifications, mostly common emitter and common collector circuit will be used. This is all about bipolar junction transistor. Thank you.